Hi everyone, it's Mr. Sinti, and today I have the pleasure to be discussing with you one of the more important statistical tests that we could ever really understand in our field of science, which is called the chi-squared test. And so this particular discussion is going to get into how to solve chi-square and maybe get even into a discussion of why it's important, and then we'll run through a couple of examples, and then hopefully you'll be able to appreciate it. And so one of the things about science is that we're in the business of collecting data, and we do that in order to try to answer questions that we have, and whether or not an hypothesis could be accepted or rejected based on the collection of that data. And so this is sort of the bread and butter of what we do in science. And so we have to ask this very important question right out of the gate, which is the data that we're collecting due to chance, or is it to one of the variables that we're studying in the particular experimental design? And so that's a very valuable point. And so it's the chi-square is used to determine whether or not the difference between what we expect and what we actually observe is significant. And so this is a statistical test to consider whether or not the data that we're collecting in terms of our observations are significant or not. And so this is what the equation looks like. And fear not, we're going to, the point of the video is to go through it. And so you might be familiar with some of these things from your background. And so let's just go through the equation of what each of these variables mean in the chi-square test, and then we'll do some examples. And so first off, this x, it's sort of a slanty looking x squared is chi. That's what we're trying to solve. This symbol right here that sort of looks like a stapler remover is the Greek letter sigma. And so this literally means the sum of something, and so we're going to be adding up some values, so it's a summation. And so O is obviously, or maybe not obviously, observed. This is the actual data that we're collecting. So the numbers that we are doing an experiment where that we're gathering, we're counting things, we're tallying, these are the observed. And so then we have expected values, and you might be thinking, how can we expect the results? We don't know. Well, in some cases we do know. And so, like for example, let me run you through this very quickly. Hopefully you have a little bit of background in this. So if you were doing a cross between pea plants and you were considering a trait such as flower color, and you were dealing with, sorry for the quick explanation of this, if you're dealing with homozygous individuals, like this would be homozygous dominant purple and homozygous recessive white, if you cross those two, you would get heterozygous plants, and you'd expected value 100% of them, because the P allele is capital is dominant over the recessive little p. And so all of the individuals are heterozygous, big P, little p, because there's always two alleles for this particular trait. And so as it turns out, when you're doing an F2 cross, and you cross the heterozygous, in other words, purple and purple, you would expect, when you look at the segregation of alleles, you would expect 3 purples to 1 white phenotypically. So that would be the expected ratio. A 3-to-1 ratio would be your expected. And so if you were actually conducting this experiment, and you're counting the number of plants in your experimental garden, and you're saying, well, it's close to 3-to-1, it's similar, I guess, or no, we're going to apply the chi-square test to determine whether or not we're close or not close. And so that's what this conversation's all about. And so it may be a little bit obscure at the moment, but hopefully it'll be, I will illuminate this. And so chi-square again looks like this. So we're going to go through this and take a look. And so let's look at a simple example first. And so one of the classic things that we could do in life is flip coins. And so here's a quarter. And if we were to flip it, as you know, there's a head side and a tail side. So the probability of getting a head or a tail is 50-50. And so this is what we expect. So in other words, if you were to flip the coin 100 times, our expected value would be 50 heads and 50 tails. But you know from maybe doing this that what you actually observe and what you expect may be slightly off. And so when we actually flip the coins, this is making up some numbers. Say it's 62, just made that up. 62 could be anything. 62 heads, 38 tails. And so the question that we have is, are the results, the observed results, due to chance, or is there something up with the coin? Are we not flipping it right, or is the something wrong with the table, or is it there's an unevenness? Is there some other variable that needs to be considered? So is it due to chance? Are these results legitimate, 62 and 38? So what I'm trying to say, although I haven't introduced this term yet, is I want to discuss with you the concept of null hypothesis. This is very, very important in science. And so chi-square is used to test the null hypothesis to see whether or not it's significant. So the null hypothesis is always something like this. There's no significant difference between the observed and the expected results. This is the null hypothesis. Okay? So in our particular discussion, so scientific experiment, the null hypothesis is sort of a general statement. It's like a default. So there's no relationship between the measured phenomena. Okay? So the two measured phenomena, there's no difference between observed and expected. And so let's talk about this a little bit. So by rejecting or disproving the null hypothesis, what you're concluding is that there are grounds for thinking that there is a relationship between some phenomena, some variable that you're testing, or some potential treatment, or the effect of something. The effect of light, the effect of water, the effect of pH, the effect of whatever you're trying to measure is having an effect on the experiment in question. Okay, so that's when you're rejecting it. So it's the central task. It's the central task of science, which gives tries to give a precise sense in which a claim is capable of being proven false. And so this is really critical, this conversation. So in this sort of statistical significance, the null hypothesis is usually in capital H with a little subscript O, and that's read as not. So it's H not. So that's how that's interpreted. So the null hypothesis is usually true. It's assumed true unless the evidence, the data that you're collecting indicates otherwise. Okay? So it's usually assumed true. This is H sub naught, or just simply H naught. So the statement being tested is the null hypothesis. So the test of significance is designed to assess, and this is the heart of the matter, the strength of the evidence against the null hypothesis. And that's what the chi-square is all about. It's a measurement of strength against the null hypothesis. Okay, so usually the null hypothesis is that there's no difference, there's no effect of the variable. Okay, and so it's when you're experimenting. I don't know, maybe this is going too far, but you're hoping that there's an effect of moisture, there's an effect of light, or there's an effect of a certain pharmaceutical, maybe, or the statement that is hoped or expected to be true instead of the null hypothesis, which is there is no effect, is what we refer to as in science as the alternative hypothesis. So we have that as H1 or H sub A. Okay, that's what we're hoping for. So when you're looking at statistical significance, very roughly, the procedure for deciding goes something like this. So you take a random sample from the population, okay? So the sample size, and the data sample is either consistent with the null hypothesis, and if it's consistent with the null hypothesis, then we do not reject the null hypothesis if there's consistency between the observed and the expected. And so what we say statistically is that we fail to reject. We fail to reject the null hypothesis. In other words, we're accepting the fact that the observed and the expected are very similar. So we fail to reject. So if the sample is inconsistent, the data is inconsistent with the null hypothesis, then we reject. We reject the null hypothesis, and then we conclude that that variable is somehow playing an effect. So the alternative hypothesis is true. So maybe we're onto something. Okay? So in our coin toss, we observe something like 62 heads and 38 tails, right? So if we know that the expected in 100 is 50 heads and 50 tails, we need to ask ourselves the question, so, is this reasonable? Is the 62 and 38 within reason? So the whole point of the chi-square is, do we accept or reject the null hypothesis that there is no effect? And so in order to actually totally solve for chi-square, let me introduce to you another concept that is very important in statistical analysis that we need at this point. It's something called degrees of freedom, or n minus 1. Let me explain this. So if you look at this function right here, do you see a plus b plus c equals 10? Now, let me assign some numerical values to this. So if I'm just making this up. So if I say a is, and again, I could make it up. I could say anything. I could say it's 100, or it's 50, or it's 4. Let me just say it's 4. If I say that a is 4, and I ask this, okay, what's b going to be? I have ultimate freedom. I can make this whatever I want. I can make this -7. I can make it 1,000. I can do anything. But let me make it simple so I can illustrate this. Let's say b is 3. Okay. So now if a is 4 and b is 3, now I just chose that because I have freedom. Okay, so do you see how this is 7? So now C, I'm locked into it because this has to equal 10. And so C must be 3. Okay, because this all adds up into 10. And so do you see how A, I could choose anything, and B, I could choose anything? I have total freedom. But then C, I've lost my freedom. And so degrees of freedom is, n, remember, is the number of data points, 1, 2, 3 of the sample set, so it's 3. So it's always the number minus 1, because the third one we don't have any freedom. Okay, so in this case, the degrees of freedom for this equation right here, degrees of freedom would be 2. If I have 8, n equals 8, my degrees of freedom would be 7, because the seventh one I wouldn't have any more freedom in terms of the outcome. So getting back to our heads and tails example, okay, since there's 2 outcomes, n is 2, really the degree of freedom is 1. So it's 2 minus 1. So it's n minus 1, which is, in this case, 2. 2 minus 1 is 1. So the degree of freedom is 1. So the reason that degrees of freedom are important is because when we look at this chi-square table, as you can see right here, what we're looking at, we need to match up degrees of freedom. So in this coin toss, the degree of freedom is 1. So we're looking right here in terms, and we're not considering any of this information. Now, the probability, this 0.05 or 5% means that we're 95% sure, and in this case 0.01 is 1%, so it's 99% sure. And then these values right here are called the critical values. I can explain that now. So you're like, well, how come, here's your question, how come degrees of freedom are always 1, 2, 3? Well, you can't have a 0 degree of freedom because there's nothing to, if you have only one outcome, there's nothing to compare. Okay, so I hope that's clear. So the next thing I want to consider is this sort of probability, again, of exceeding the critical value. That's what I want to get into. These are the critical values. These are the degrees of freedom. This is the probability. Okay, so again, let me interpret the probability. So 0.05, which is kind of a standard in science, and at least in my interpretation and my experience in science, is that usually when you're 95% sure, that's confidence enough, because that's what we're talking about. That's confidence enough to either accept or reject the null hypothesis. So we're often looking at this right here, this 0.05. This is an area. This is where I'm coming up with this. This means 95% sure whether or not we're accepting or rejecting. And so the critical value in this case, since the degree of freedom was 1, and we're looking right here, so we're right here. So the critical value is 3.84. So this is very important. So when we do the calculation, and we will in a second, when we do the calculation for chi-square, and you get a number that's higher, larger than 3.84, then you reject the null hypothesis. You reject it, okay? And then in this case, if it's less than 3.84, then we're going to accept the null hypothesis. Although it's, again, I said this before, it's better to say we fail to reject it. We fail to reject it if it's less than 3.84. Okay? So let's go through this example. So the null hypothesis, again, means, let me sort of like kick this around here. Let's go white. So the null hypothesis is there's no difference between what observed and what's expected. Okay, this is the null hypothesis. So again, if we flip a coin, let's do something different. Let's flip the coin 50 times. So if we flip heads and tails 50 times, what do we expect? We expect 25 heads and 25 tails. Okay, so that's the heads and this is the tail. This is what we expect. This is the little e. Okay, so what's the observed? I'm just making this up. Say it's 28 heads and 22 tails. So is that significantly acceptable? This is what we're saying. And so when we try to do this, we say, okay, chi-square is equal to the summation. Okay, so what we really want to start calculating is this up here. So observed minus expected. So we go observed minus expected. So that's 28 minus what we expect is 25 right there, and then we'll square that, and then divided by expected, which is 25. So that's for the heads, and then tails is what did we say here? 22 minus 25, and then we square that over 25. Okay, and then since it's a summation, we add these two together. So let me just do the math. I took the time to do it over here. So it's 9 divided by 25. And then this is also, interestingly, 9 divided by 25. And then when you add this up, it's 18 divided by 25, which is equal to 0.72. Hopefully I've done that correctly. So, okay, what is that? Okay, so 0.72. So we come down on the chart here and we say, okay, what's up? So on the chart, again, n minus 1 degree of freedom, since there's 2 outcomes, is equal to 1. So here it is, and this is what we're looking at, 0.05. And so we ask ourselves the question, is 0.72 greater or lesser than 3.84? And I think you know that it is less. Okay? So here is another example. Okay, so here's a red blood cell. Erythrocyte carries oxygen through the body, most common cell in the body. One of the things about this red blood cells is that they have different phenotypes. You might be familiar with it. You can have A blood, you could have B blood, you can have AB blood, and you can have O blood. Okay, so there's 4 possible outcomes. All right, 4 outcomes, 4 phenotypes. And so the genetics of this, I don't want to go too far with the genetics, though it's totally interesting. Let's say that the mother of a child is type A blood. And so they have a dominant allele and a recessive allele. And they marry a father who is B blood, okay? And they're also heterozygous. And you're like, well, what are the possibilities of the outcome for the children? Well, one child could have AB blood, another child could have A blood from this Another child could have B blood, and then another one would have O blood. So there's 4 possible phenotypic outcomes from this. All right? And so let's say that there are 120 in this sample population. So we're sampling this group, and there's 120, and this is these are the numbers. 26 of them have A blood, 31 have B blood, 39 have AB, and 24 have O blood. Okay, out of the 120. Now, you might be thinking, out of 120, these are the observed. Okay, so that's observed. So you might be thinking, well, what is the point? What are we doing? So the chi-square, again, analysis is trying to compare the tallies or the counts, that sort of the categorical responses to these are independent groups. And so we're trying to figure out if this is statistically valid. Now, we would expect, again, since I was showing you that we expect that each of those 4 phenotypes would appear equally, like 1 to 1 to 1 to 1, or in other words, 25%. So if there's 120 in the group, then we would divide that by 4, and you'd expect that the expected values would be 30. So do you see back here? These are the observed. This is the observed. The expected would be that each of these would be 30 if it came out like that. That would be quite remarkable if it did that. So, but we're asking ourselves, like, is this acceptable that these numbers are there? Is this ratio significant? In other words, 1 to 1 to 1 to 1. Would we expect that? Okay, so here's the observed, and so this chart is fairly useful. You could pause the video at this moment and sort of, redraw this or contemplate this a little bit. So I like it like this because you can really solve the chi-square easily. So do you see this expected? So again, you would expect this to be 30, okay, since there's 120, and this is a 1 to 1 to 1 to 1, okay? So when you do this, when you're solving the chi-square, the observed minus the expected, if you do the math on this, so it's 26 minus 30, and this one is 31 minus, so I've done this for you. So do you see how these are the results here? Now you would want to square that. So you do the parentheses first, and then you square this, so calculator might be needed. So when you square this, you get 16 for this value, 1, 81, and 36. Okay? And then when you divide it, you divide that by expected, you then come up with this. You get these numbers, 16 divided by 30, that's the expected. It's 1 divided by the 30, you get this. And then the summation is simply you add all these guys together. So it's 0.53 plus 0.03 plus 0.27 plus 1.2, and the answer is 4.46. Okay, so this is our chi-square. The chi-square is equal to 4.46. And so here's our question. What is our degrees of freedom? Since there's 4 outcomes, 4 phenotypes, it's really 4 minus 1. So the degrees of freedom are 3. Okay. So when you look at the chart, you say, okay, 1, 2, 3. So there we are. And again, here's our probability of 95% confidence. Okay. So here's the value. The value that we found is 4.46. Now, is it larger or smaller than the 7.8? Well, it's smaller than it. It's smaller than 7 points. So that shows that any difference in the results are due to chance. So which means that the null hypothesis is accepted since it's smaller. So in other words, we fail to reject the null hypothesis. Okay, so these numbers are fine, in other words. So again, to remind you, a number higher, we have to reject the null hypothesis, and if it's less, we accept or fail to reject. So hopefully this was illuminating and helped you a little bit understand chi-square. So the truth is, it's a really cool test. It's very important that we understand this, and so really the best way of understanding it is just simply practicing it as often as you can. And so hopefully this was valuable and that you learned something. Thank you for watching.